trend is as you go across a period in the periodic table, what's happening? Are the atoms getting smaller? Are electrons becoming more difficult to remove or easier to remove? And as you go down a column in the periodic table, what happens? So as you go from hydrogen to lithium to sodium to potassium, what happens to how hard it is to remove an electron, how large the atom is? Those are trends. We're going to look at atomic radius, ionization energy, electronegativity, and electron affinity. That might be the second movie though. So all the trends are going to depend on two things. What we're looking at is pretty much how attracted is that electron, is the outermost electron to the nucleus. And the two things that are going to affect that, most important, is going to be the number of electrons shielding, because the more electrons there are in the way, the more shielding there is, and the number of protons. So the protons one, let's start with the shielding is the most important thing to look at. The more electrons you have shielding, the less attraction there are for those electrons to the nucleus. So we're always looking at, how hard would it be to remove an electron? You're going to remove the outer electron. It's the farthest away, it has the least attraction, it's the easiest to remove. So if I had a situation where I have one electron out there, two core electrons moving around, what affects how easy it is for me to remove that electron is going to be how many protons are in the center and how many electrons are shielding this outermost electron. So you can think of shielding as, like, if you're at a concert. When you're in the front row, it's great, you're right there, you get to see everything. The better the concert is, the more attracted you are to the concert. So your second row, that's still pretty good. And as you get farther and farther back, you can see the show less and less. It really doesn't matter if anybody else is also in your row because they're not blocking you. So if this is me, I really don't care if other people are sitting beside me, that's fine. It's just how many people are sitting in front. It's going to block my view. So shielding electrons is electrons that are on inner cores that are moving around and blocking the attraction between this negative electron on the outside and the inner and the positive nucleus. So more shielding, less attraction. Second thing we look at that affects how easy is it to remove this outer electron, or how attracted is this outer electron to the nucleus, is how many protons are in there. The more protons you have, the more attraction there's going to be for the outer electron to the nucleus because you have a stronger positive charge. So there's a couple small things to look at. These are the two main ones. I look at this first. Shielding is the number one most important. Then number of protons, if the shielding is the same, could tell you which outer electron is more attracted to its nucleus. After that, things to look at, if you're not following the trend you'd expect to follow predicted by these two, then you have to start looking at what is affecting electron stability. Do you have electron-electron repulsion? Is there a lower energy level location as in S versus P? If there's no electron-electron repulsion, you'll have a more stable electron that's more attracted to the nucleus. And if you're at lower energy locations, the S versus the P, you're also more attracted. Let's see. And so all these trends are based on how attracted the outermost electrons are to the nucleus. So let's look at a couple. See which one attracts it the most. So the easiest way to see this is to just draw the Bohr models for these. So I'll look at calcium and I'll look at potassium. Calcium has 20 electrons. It has 20 protons in the center, 20 positive, and then it's going to have 2 electrons on that first shell. It's going to have 8 electrons on that second shell, right? And then it's going to have 8 electrons on the third shell, and it's actually going to have 2 electrons on the fourth. So there's going to be 2 electrons on this outer shell. And if you want to know where that came from, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So just the electron configuration, and that gives me 2, 4, 10, 12, 18, 20. So 20 electrons. So there's potassium with its 20 protons and its 20 electrons. And I'll look at, I said potassium, I meant calcium. Potassium has 19 protons and electrons, so 19 positive things in the center. And then it's going to have 2 electrons here 8 electrons on the next shell. Whole thing's going to be the same except for 1 electron on the outside instead of 2. And 1 electron on the very outside, I'll put it here. So our question is, which electron is more attracted to the nucleus? The outer electron on calcium or the outer electron on potassium? And we said the two things we look at, that we always look at, are going to be number 1, number of shielding electrons, number 2, number of protons. So for shielding electrons, let's go like this. So the number of shielding electrons is going to be, I have 10, 18 electrons blocking this guy. So for the potassium, there's 18 electrons blocking. And for this guy, I've got also 18 electrons blocking. Because this one doesn't block. This is somebody sitting next to you at the concert, not sitting in front of you. Can't really complain about them blocking your view. So there's 18 shielding electrons for both. Based on the number of shells, the attraction for the outer electron to the nucleus is the same. So we look at number of protons for each one. And that's easy to see that there's 20 protons in the calcium versus 19 positive protons in the potassium. So this 20 protons is attracting, they're attracting this outer electron more than the 19 protons here. So which atom attracts its outermost electron, or the outer electron the most? Calcium. Now we look at sodium versus potassium. So sodium has 11 protons, and it's going to have 11 electrons, so 2 on the first shell, 8 on the second shell, and then on that third outermost shell there's just 1. So I'm looking at how attracted this outer electron is to its nucleus versus how attracted is this outermost electron to this nucleus. We said the first thing we look at is shielding electrons. This guy has 10 shielding electrons versus potassium's 18 shielding electrons. So since there's more shells, there's more electrons that are preventing this outermost electron from the Z, or from seeing the charge of the nucleus. And that's called the Z effective. The Z effective is the charge felt by the outer electrons to the nucleus, taking into account the number of protons and the shielding electrons. So more shells of electrons in this guy means there's more blocking of that outer negative electron to the positive nucleus charge. Alright, so which one attracts its outermost electrons the most? The one that has fewer shells. I would rather be in the 3rd row of a concert than the 4th row, especially if there's lots of tall people. So sodium attracts its outer electrons the most. So these two major trends almost explain everything, but there's a couple ways we can break them, and we've got time. Good. So they almost explain everything, but there's a few things that we should look for. So the two major trends are that attraction for outer electrons decreases down the periodic table. So as you go down, there's less and less attraction, and that's because you have a whole extra shell of electrons every time you go down. So every new period, another shell. So there's more blocking of the outer electrons to the nucleus. The second trend is attraction increases across the periodic table. And that's because you're keeping the number of shielding electrons the same, and you're just adding more and more protons. So, it's kind of like you have more and more people sitting next to you at the concert. They're not blocking you. You're not going a row further back or farther back. You're just having more people sitting beside you, and the concert's getting better and better. There's more and more protons, because we're always looking at how many protons are in the center to attract any electrons that are on the outside. How many electrons are blocking it. So two major trends. So let's look at a couple more. So we've got phosphorus versus silicon. So phosphorus has 15 protons. I'm going to draw the Bohr model again. 15 protons, and so it's going to have 15 electrons. 2 on the first shell, 8 on the second shell, and so I'm up to 10. I'm going to need 5 more, so 5 on the third shell. So we're looking at any one of these 5 outer electrons. We're saying, how attracted is this electron to the nucleus versus for silicon we have 14. So it's going to be 14 protons, 14 electrons, so 2 on the first, 8 on the second, 4 on the third. And the first thing we look at is shielding electrons. There are 10 shielding electrons for the phosphorus, and there's 10 shielding electrons for the silicon. So they're the same based on the shielding, they have the same number of shells. So then you look at the protons, 15 protons versus 14. Well, positive 15 charge is more attractive for that outer electron than the positive 14. So this is going to attract its electrons the most. So phosphorus attracts the most between those two. And then phosphorus versus arsenic. Actually, I'm just going to use the trend I just taught you. That attraction increases as you go across because there's more protons in the same number of shells. It decreases as you go down because there's an entire new shell. Arsenic is below phosphorus in the periodic table. So that extra shell of electrons blocking the outer electron in arsenic is going to lower the attraction that arsenic has. So phosphorus is going to attract its electrons, outermost electrons, more than the arsenic. And then there's two ways that these trends, actually three. The two general trends can be disrupted in three ways. The first is electron-electron repulsion, and there's no way there's time in this video for this one.